Well, hello, everybody.
Hi there.
Redox lecture number 5. We're going to hit up spontaneous reactions today. And we're going to be using that activity series, Table J, again. This kind of reference table has come back to us 3 or 4 times this year. We did it with acids and bases. What else did we do it with?
Ooh, good question.
Definitely acids and bases. We decided which metals would react with acid.
Yes, we did.
And now we're going to be using it to decide if a single replacement reaction is going to be spontaneous or not.
Will it go all by itself, or does it need a nudge?
Yeah, exactly. So here's some of the uses of the activity series. It lists metals based upon their reactivity. So the most active metals are up at the top. The least active are down at the bottom. So it's really, really kind of simple. You might notice that H2 is in here towards the bottom. That's only for comparison against acids, metals versus acids. So it's in there so you know if a metal is going to react with acid or not. But
that's not this unit.
We really don't ever mess with the non-metal side, right?
Very rarely. I think
very
once
rarely.
they mentioned it once as a part 1 question. But so here's how it works. Ready? The metal above is always more reactive. So you're going to be given 2 metals. You find them on there. The one that's higher is the most reactive.
Exactly.
That's really it.
Mm-hmm. Oh, what is a spontaneous reaction? I showed my students one today.
Oh, did you?
Yeah, I took some magnesium and mixed it with copper chloride solution.
Oh, I think I have those 2 things.
Yes, you should do it. It's very cool.
Oh, remind me.
Mm-hmm. And so I showed a spontaneous reaction, and it went forward without any additional energy. It just goes. It's like a chemical reaction you're familiar with. You mix these 2 things, and that stuff starts showing up.
Right. But so for the practical purposes for us, we have a single replacement reaction. You're going to have this lone metal and this compound.
Mm-hmm.
And the rule is if the lone metal is above the metal in the compound that we're seeing, then it is spontaneous.
Exactly.
So there, you're right. It's that simple.
And the way it works is that lone metal is more active than the one that's in the compound. So it's going to kick that one out and say, hey, I want those anions instead of yous. Get out of here.
Right. Non-spontaneous is the opposite. It's a reaction that will not happen by itself. It needs energy to go forward. Mm-hmm. And what we end up finding is that lone metal that's by itself is actually below the metal that's bonded in the compound on the chart J.
Yep. And if you mix those 2 situations together, nothing's going to happen. No reaction.
Right.
Because you have to put in energy to make it go.
And so we just discussed now how to do this. Mm-hmm. Let's do a few examples and we'll see.
I'll do 3, you'll do 3?
Okay.
Cool. Who you want to start or me?
It's up to you. It doesn't.
I'll start.
Okay.
Cool. So complete the products of the reactions that are spontaneous. If the reactivities indicate the reaction is non-spontaneous, write no.
So
reaction.
First, we got Zn plus lead chloride. Can you identify the 2 metals for us? Excellent. Now, using table J, can we find them? You can find it right on Smartboard.
So Zn, let's see. Zn is somewhere in the middle underneath Mn. So
there's Zn. And then where's Pb, above it or below it?
Pb is down below. So zinc is more reactive than lead.
And by rule, if the lone element or the lone metal is more reactive than the one that's bonded, it is spontaneous and will go. Mm-hmm. So we can go ahead and do the single replacement reaction because we found out that Zn is above Pb. So Zn is going to hook up with the Cl. Pb is going to be kicked off, and that's how we do that.
Yep.
The fact that we even show that it happens makes it spontaneous.
Exactly. Now I have to compare zinc and barium.
Okay, so let's erase those.
These ones.
There's zinc and barium.
That's what I'm going to do now. So I'm going to get rid of that one.
And on the chart too, sir?
Oh, yes. Thank you. Zinc, well, I know where zinc is. Barium. Oh, barium.
There we go.
Wonder
if that thing's coming up over our faces.
No, it's fine.
There it goes.
Oops. So barium, we found out, is more active than zinc, which means it wants to be in a compound more than zinc does.
This is the second scenario where we are non-spontaneous, so you don't have to fill in anything here at all. Non-spontaneous, right? No reaction. It will not happen unless it has the required energy to go forth.
If you heated it up or did anything according to collision theory, it might go forward.
But again, that's adding the energy to make it go, and that's non-spontaneous. Right. Spontaneous goes all by itself because it's happy to go. All right, next 2 metals. I see calcium and I see chromium.
Okay, let me see.
I'm going to find Ca and Cr.
Chromium's there right in the middle.
Good. That's the first one we should actually find. Then is Ca above it or below it?
Calcium's above it.
So if the lone metal is above the bonded metal, it will boom react because calcium is more active and will go ahead and kick chromium out of there. So now we can finish our single replacement reaction.
Boom.
And we are done.
Yeah.
Because it's spontaneous. Sure.
All right. So I'll get rid of those things. Thanks. So all he's going to do now is compare manganese, Mn, to nickel and decide if manganese is more active than nickel, it'll kick nickel out of the compound and take its spot.
Where is nickel?
Nickel
Down
is
by
towards the
CO.
bottom.
So nickel is below manganese.
Mm-hmm. So manganese is more active than nickel, so it will take nickel's spot and kick nickel out to become pure element. There it is.
Good.
Mm-hmm. There you have it.
Okay.
Now he's just going to do the same exact thing for iron, Fe, versus magnesium. So Fe's right there, Mg's right there. So find Fe on our chart. Let's see.
See Mg by
Oh.
Na.
Mg's very active.
Yeah, and Fe
iron
Fe's way down there, so he's less active.
Right. So iron is not active enough to kick magnesium out and replace it in this compound. So no reaction would occur. That's not to say if you didn't heat it up or add a catalyst that a reaction wouldn't occur, but this is no spontaneous reactions would occur. It won't just react automatically. Now, cobalt and lead.
Okay,
Cobalt.
I'm gonna try and find lead first. I like to find the second one first.
Okay.
Then I know if the first one is more reactive, right?
Yeah.
So now when I find cobalt, if it's above it, I know what to do, right? If
Exactly.
I find cobalt and it's above, I know it's more reactive.
So cobalt is much more reactive than lead. And as a matter of fact, lead is a very unactive metal. That's why they used to use it for pipes and drains and all that kind of stuff. It stuck around for a long time, didn't react with your water or your atmosphere. But it is active enough
To make it go nuts.
sometimes, yeah. If you had copper, silver, or gold,
Those are the precious metals.
those would react with this particular compound, and lead would replace them.
True, but we call them the precious ones because they don't react with many things at all. They don't oxidize easily.
And that's why they're good for things like wires and all that other kind of stuff.
And jewelry.
Jewelry and wires. The fact that your jewelry doesn't turn green or get a tarnish or oxidize means that it's very not active.
Yeah.
So that's why we
It's
have
unreactive, which is what we want.
metals that are precious, are very not reactive. They don't oxidize and they don't engage in oxidation and reduction. They won't go through
It's
single
not just that
replacement
they're
reactions.
rare; it's that they actually last a long time.
Oh, absolutely. So
And guess what?
that's it.
Go ahead and say it.
That's all, folks. See you later. Discard my annotations. Let's see if we can finish this.